One of the properties of atoms that has periodic characteristics, in other words, changes in a regular fashion as a function of position on the periodic table for each element, is ionization energy. In this movie, what I'm going to do is cover some of the characteristics of ionization energy, first defining that particular property and what it means, then discuss the trends in ionization energy as a function of position in the periodic table, and then finally discuss what the trends reveal about the electronic structure of the atom. So in other words, what do the trends in ionization energies reveal about how the electrons are arranged in the atoms across the periodic table. So first, define ionization energy. This is the energy required to remove an electron from a gaseous ion or atom. So we're basically ripping an electron away from any particular atom in the gas phase, and that defines the ionization energy. So for example, beryllium in the gas phase, beryllium is normally a solid at room temperature, but assuming we heat it up enough to go into the gas phase and then remove an electron, right, and that's represented by beryllium gas on the left-hand side of the equation, and then on the right-hand side an electron, a free electron, and of course that electron must have come from the beryllium that's on the left-hand side. That would leave the beryllium now with a positive charge because it has one less electron associated with it. Right? So one electron down means it has a slight excess of protons in its nucleus compared to surrounding electrons, and will have a +1 charge. For each electron you remove, in fact, the charge on the atom will go up by 1. Now, this requires a certain amount of energy, which is called ionization energy, and for the first electron removed, we call it the first ionization energy. Now, this is an energy requiring process, and the reason is because the electrons, being negatively charged, are strongly attracted to the nucleus, which has a positive charge. So those are those attractions. If I want to remove an electron, that's going to require the input of some energy, which is equal to the ionization energy. And that will change as a function of the type of atom which we are removing the electron from, and how many protons it has in its nucleus, and also its position on the periodic table. So, if we go on to remove another electron from this now beryllium +1 in a successive ionization, the beryllium +1 will go up in charge to +2 in removing that second electron. And of course, this is the second ionization, and our second ionization energy. This second step will always require more energy. And the reason is because we are removing a negatively charged electron here from an already positively charged ion. And that's going to require more energy. Now, trends in first ionization energies are quite revealing and can be helpful in understanding the electronic structure of atoms across the periodic table. So if we look at this plot, which shows ionization energy for all the elements in the periodic table as a function of atomic number Z. So in other words, as we go across the periodic table from hydrogen, which has 1 proton, Z = 1, to helium with Z = 2, down to lithium with Z = 3, to beryllium with Z = 4, and so forth across the x-axis. And we show the first ionization energy for each of those atoms on the y-axis. And so you can see this sort of jagged-looking graph in which the ionization energies go up and then drop down, right? Go up and then drop down, up and down, and so forth. If we sketch out a few of the atoms on the periodic table to help us remember the structure of the periodic table, it looks like this: hydrogen to helium, lithium through neon in that period, and then finally sodium through argon. We can see some trends that follow the periods within the periodic table. So if we look from hydrogen to helium, right here, we see there's a big jump in the ionization energy. And similarly, from lithium to neon, we see a somewhat regular trend, an increase in the ionization energy. In other words, an increase in the energy required to remove an electron. And that, of course, follows for sodium through argon, the next period down the periodic table. And roughly throughout the periodic table, we see this trend. Okay, so across this period, hydrogen, helium, and through the next two, we see an increase in ionization energy from left to right, up. Okay, IE is abbreviation for ionization energy. Now, if we look at the different families, so for instance, I'm highlighting now in blue, helium, neon, argon, krypton. Notice in general, the ionization energy there is decreasing as we go down that family. So down a family, the ionization energy generally decreases. It gets easier to remove an electron. That trend holds for the family of the fluorine family, right? The halogens, fluorine, chlorine, bromine. If we went on to iodine, we would see that decrease, right? It's not a perfectly regular decrease in ionization energy, but it is decreasing. Similarly, nitrogen to phosphorus, right, to arsenic, and so forth, we see a regular decreasing trend in the ionization energies. And so the trends, if we sum up, are increasing ionization energy, increasing energy required to remove electron from left to right, and decreasing ionization energy going down a family. Sometimes I will just summarize it as the ionization energy increases up and to the right across the periodic table, which means that the element with the highest ionization energy is going to be helium, right, shown in the periodic table, because it is furthest up and to the right on the periodic table. Trends in successive ionization energies also are revealing about electronic structure. This table from your textbook shows ionization energies in attajoules, right? So ionization 1, 2, 3, 4, so successive removal of electrons, and the energies required to do that. So, for instance, the energy required to remove an electron from hydrogen, 2.1 attajoules, joule being the unit of energy. Helium requires 3.94 attajoules, and then 8.72 attajoules of energy to remove the second electron. Notice again, as we pointed out before for beryllium, the first electron requires energy, right, input of energy to remove that negatively charged electron, separate it from the positively charged nucleus. It takes even more for the second one because now our helium will have a +1 charge on it, and it's more difficult to remove that second electron. If we plot these successive ionization energies, we can get some idea about the electronic structure of the arrangement of the electrons in the atoms. So looking at beryllium, for instance, we plot the first two ionization energies, right, there. And then when we further remove a third and fourth electron, notice that the ionization energy jumps up even more dramatically. And we can see sort of two successive trends, right? A sort of lower ionization energy, an easier region to remove electrons, and then a more difficult, harder region or more energy requiring region to remove electrons for the third and fourth. And of course, this is not just due to the fact that the beryllium is going from neutral to +1 to +2 to +3. Because if that were the case, we would expect the trend to be a little more regular and not to have this sort of big jump, okay, that's shown here in the ionization energy. This arrangement of energies required to remove electrons indicates that the electrons are arranged in shells. So we have an outer shell in which the electrons are, in general, further away from the nucleus and therefore easier to remove, and an inner shell of electrons in which the electrons are closer to the nucleus, therefore more strongly attracted because they're more close to they're closer to the positive charge of the nucleus, and therefore require more energy to remove. If we look at the periodic table, we can understand this shell-like structure by simply looking at the periods going from left to right across a periodic table. So, for instance, looking at beryllium we know has 4 electrons. The neutral beryllium atom has 4 electrons. Beryllium is shown here, right here in the periodic table. Right, it has, if we just count 1, 2, 3, 4 electrons, if we just think each step as being adding a new electron, a new proton to our atom, right, we get the beryllium with 4 each. Okay, the first electron I remove requires a little bit of energy. The second electron I remove requires a little bit more. And now notice in the next step, when I remove more electrons, I'm removing the electrons that were sort of normally associated, also with this position on the periodic table, the helium and the hydrogen. And in fact, we can think of this shell-like structure as being associated with each step in the periodic table. So, even more revealing is to look at the structure, electronic structure of potassium, these successive ionization energies for potassium. Notice we have 1 electron here, the lowest in energy, easiest to remove. That indicates it's probably the furthest away from the nucleus. And so I'm going to count that as this position, right? This last electron that I'm adding in as I get to potassium in the periodic table. Now as I remove more electrons, it indicates they're higher in energy, which means that they may be in a shell that on average is the electrons are closer to the nucleus and therefore harder to remove. And so I'm going to associate that inner shell with the next step up in my periodic table. So those 8 electrons, right, correspond to the 8 positions, the 8 steps across the periodic table in going from sodium across to argon. Right? And then the next 8 electrons correspond to the next step in the periodic table. And then finally, removing 2 more electrons requires the most energy from that potassium and indicates a new shell. And that new shell has just 2 electrons associated with it. So, what can I say about the electronic structure in potassium? I have 2 electrons with very high energy, right? And 2 steps in the periodic table. So that is the first innermost shell of electrons associated with potassium. Then I go, whoops, got a little ahead there. Then I go down to the next shell of electrons, 8, right? A slightly further out, but still very close to the nucleus, requiring a certain amount of energy, high energy to remove. Then next 8 electrons stepping across the periodic table, and that shell of 8 electrons. And then finally the last electron associated with potassium, which must be the furthest out. Now that outer electron, that electron that is in the outermost shell of the atom, is called a valence electron. And we're going to come back to that in just a second. But we always remember that the outermost shell of electrons are called the valence electron. That's going to be an important term. The inner electrons we're going to call the core electrons. And the core electrons, as you can see from this diagram, this energy diagram, are tougher to remove, and that's because they are in general closer to the nucleus. Moving on, back to the valence electrons. The Lewis dot representation, or the outer shell or valence electrons, is often represented with what is called the Lewis dot representation. You've probably seen this in your high school class. Okay, so if we're looking at, for instance, this row right here, okay, sodium through argon, okay, and sodium, right, is the first atom in that particular row, and therefore it has only one electron in that shell, right? And remember that each row is going to represent a shell of electrons. So we've got a shell of 2 electrons, a shell of 8 electrons, another shell of 8 electrons. Sodium has 1 electron in that shell, and if we were to look at its ionization energy, we see that the energy required to remove this first electron would be the lowest. It's the easiest to remove. Then once we start removing electrons from this inner shell, the energy is going to go up, just as we observed with potassium. But for just the valence electron, for sodium, we can represent the valence electron on the sodium atom with just a single dot. And so that dot represents that one valence electron, that one electron sodium has in its outer shell. Magnesium, being in the second position in that particular row, has 2 valence electrons. In other words, 2 electrons in that shell. So we would expect, if we looked at the successive ionization energies for magnesium, that we would have 2 electrons that were generally easy to remove. And then once we went to try and remove from that second electron, we tried to remove the third electron, we'd see a significant jump in the ionization energy as we go to try and remove electrons from an innermost shell of the magnesium. Aluminum, being the third over, has 3, and so we represent its valence electrons with 3 dots. Silicon, 4th position over, and therefore has 4 electrons in that shell. Phosphorus, 5 electrons, and so forth. Sulfur will have 6, chlorine 7, and argon 8. And once we have added 4, we start pairing them up. As you see, I've done here with the phosphorus. 1, 2, 3, 4, and the 5th one I pair up. If we look at further up the periodic table, lithium has 1 electron in its outermost shell, because it's the first atom in that period of the periodic table. And so we can represent that 1 valence electron with a single dot. Moving across to beryllium has 2 in its valence shell. Boron 3, carbon 4, nitrogen 5. And what you should notice here is that you should start to see a pattern. If we took this out further, we would see it go on further, that all atoms in the first column of the periodic table will all have 1 electron in their valence shell. And all atoms in the second column of the periodic table, beryllium through magnesium through calcium, will have 2 electrons in their valence shell, so 2 outermost electrons. When we go across to boron and aluminum, this family here, we see that they have 3, and we expect then that we're going to have also 3 electrons for gallium and indium and so forth. Carbon has 4 valence electrons, as well as silicon, as well as germanium, as well as tin, and so forth. So we see this reoccurring structure of valence electrons for families in the periodic table, and of course this is going to explain some of the similar properties that we have observed for certain elements, for elements in certain families. So if you remember from our class a few days ago, we watched the movies of the reaction of lithium and sodium and potassium reacting with water, and they all had similar reactions, although some slightly more violent than others. But the reactivity was very similar, and this is a direct effect of the fact that each of those atoms has 1 electron in their valence shell.